Welcome back, students. In this video segment, we will talk about one section, section 2.3, entitled Linear Independence and Bases. Before we get started, a couple of things to note. First, this is a very long and very involved section and should not be attempted before you've had a chance to look at some, if not most, of the homework from the previous section. It's not a good idea to go directly from section 2.2 into 2.3 without some level of mastery in the materials in the previous section, okay? Also, I'm going to give you a little bit of a warm-up for this section. So you may be able to skip forward in the video if you want to skip the warm-up, but I don't recommend it. So by a warm-up, I mean I want to bring us up to speed in terms of where we are in the text. So let's do that. In section 2.1, I gave you an introduction to the concept of a vector space. A vector space, which I can't spell here. A vector space is a non-empty set of objects called vectors that satisfy a properties, and on that set is defined an addition, we call vector addition, and scalar multiplication. Okay, in section 2.2, what we were primarily interested in is a subset of a vector space, a very specific kind of subset of a vector space. Okay, that subset is called a subspace. A subspace is a non-empty subset of a vector space that itself forms a vector space under the same operations of addition, vector addition, and scalar multiplication. So if in this rectangle that I've drawn we have V, the vector space, then a subspace is, we'll say S, and I'm going to abbreviate subspace as SS with your permission. And we need three things to happen. We determined that we need three things to happen for this subset to be a vector space. We need this set to be non-empty, and we need closure properties to hold true. Closure under addition. Let me do this. Closure under addition, and closure under scalar multiplication. Scalar multiplication. We determined that if we have those three things happening, that the subset of the vector space V definitely is a subspace. That is itself a vector space under the additions from V of addition and scalar multiplication. Okay, in that same section 2.2, we also talked about linear combinations. Linear combinations. Again, we're not talking about section 2.3 yet. This is just sort of a warm-up, a recap, if you will, of what we've done with vector spaces so far. Okay, linear combinations are nothing more than objects like this. So if V1, V2, let's say all the way up to Vn, are elements of V, a vector space, then C1 V1 plus C2 V2 plus ... all the way up to Cn Vn is a linear combination. Linear combination of the vectors V1, V2, all the way up to Vn. Okay. And also in that section, we talked about the span of the vectors V1, V2, ... all the way up to Vn. And if you'll recall, we used the word span as a noun and span as a verb. This tends to cause a few problems with students just beginning with this stuff. So span as a noun, as an object, it's the set of all vectors from your vector space. It's the set of all v in the vector space such that v is a linear combination of those vectors. So it's a set of all vectors from the vector space that can be written as a linear combination, some linear combination of the vectors from the vectors v1 to vn. Okay. We also determined that span, the span of v1, v2, all the way up to vn, is a subspace of the vector space V. Okay. Then we looked at span as a verb, as an action word. Okay. Let's see. We say that vectors v1, v2, all the way up to vn, they span v, the vector space, if the span as a noun, the span of v1, v2, all the way up to vn, equals the whole vector space. Okay, so let's try to piece together what we mean by these two usages of the word span. So generally, if you have a vector space, the span of a set of vectors, that is the set of all linear combinations of those n vectors, the span of v1, v2, all the way up to vn, that span is a subspace of the vector space V. It doesn't cover the whole vector space. It doesn't include the whole vector space. But when it does, if the span of those vectors covers the entire vector space, that is, if the span of those vectors equals the entire vector space, then those vectors, those n vectors, are said to span the vector space V. Sometimes you can think, or in other words, you can think about it as if the vectors v1 to vn, they completely cover the vector space V by taking different linear combinations. Okay, so again, the span of a set of vectors, v1 to vn, is a subspace. Generally, that's a noun, is a subspace, forms that little blob that I have, that little puddle that I have in the vector space. But if that span happens to cover the whole vector space, if the puddle covers the entire vector space V, then we say that those n vectors, they span the vector space. Okay. Again, this is just a warm-up. This is just a recap. I would not attempt to engage yourself in the lecture for section 2.3 unless you've completed the majority of the homework for section 2.2. It's not a good idea. I think it will only tend to confuse you. Okay. All right. So let's start section 2.3. Let's start section 2.3. Okay. Let's begin 2.3 with some spanning sets for 2.3. Some spanning sets for R2. So here are some typical spanning sets for R2. Some spanning sets for R2. Okay, and what does that mean again? It means every element of R2, every point in the xy plane, if you want, can be written as a linear combination of elements from these spanning sets. So one spanning set would be the column vector 1, 0, and 0, 1. These two vectors form a spanning set, a very common one. They're called the standard basis vectors for R2. You're used to them if you had Calc 3 or physics. You're used to calling them the unit vectors I and j, or you could write them in bracket notation 0, 1, 1, 0, and 0, 1. But they, nonetheless, they span, as a verb, they span R2. Every vector in R2 can be written as linear combinations of these two vectors. There are many spanning sets for R2. Another spanning set would be the column vectors 1, 1 and 2, 0. These two vectors form a spanning set. Every vector in R2 can be written as a linear combination of these vectors. They're kind of a strange spanning set, but they nonetheless span R2. They completely cover R2 by linear combinations. Another set looks like includes the standard basis vectors, but also the vector 1, 2. Every vector in R2, every single vector in R2 can be written as a linear combination of these three vectors. Okay, it seems like we have somehow too many vectors in that set. I don't know why we'd call it too many, but it seems like, if we could have fewer vectors in our spanning set, it seems like that would be more efficient. I'm letting a cat out of the bag really early. It is more efficient to have a fewer number of vectors in your spanning set. So let's hold off on that concept for right now. So here's a question. It looks like I've produced three spanning sets for R2. Three sets of vectors, each of which completely span R2. The standard basis vectors, two other vectors, and a set with three vectors in it. So question, can a spanning set for R2 have only one vector? Only one vector in it. It's a legitimate question. It's quite a legitimate question. What it's leading to is the core of this section. We're interested in interesting. We are interesting also, but we are interested in what's called a minimal spanning set for a vector space. And what we mean by a minimal spanning set, this is a huge, huge deal for us. A minimal spanning set is we're looking for a spanning set of minimal size. What that means to us right now is the spanning set, the third spanning set that I introduced us to, is not a minimal spanning set, because there are other spanning sets that have fewer vectors in it, namely two vectors. And then there's my question, well, can we do better? Can we write any vector in R2 as a linear combination of only one vector? Okay, well, the answer is no. We can't do that. But we don't have any theory to back that up, to back up what I just said. We are interested in, this is the primary purpose in this section, is we're interested in a minimal spanning set for vector space. That is a spanning set with as few vectors as possible, and the theory that goes along with those minimal spanning sets. Okay. Now, back to that spanning set with three elements in it. So back to the spanning set for R2 that has the vectors 1, 0, 0, 1, and that sort of extra 1, 2. I want you to notice something. Notice that that third vector, 1, 2, that third vector can be written as 1 times 1, 0 plus 2 times 0, 1. Now look at that very carefully. One vector is a, and I'm going to start abbreviating linear combination for LC, linear combination, because we're going to be saying this really often. So one vector is a linear combination of the others. Again, we have a spanning set for R2, which means every single point in R2 can be written as some linear combination of these three vectors. But one of those vectors is a linear combination of the other two. Okay? And what that means is that those three vectors, this means something really important for us. This means that the vectors 1, 0, 0, 1, and 1, 2 are called linearly dependent. They are called linearly dependent. Okay. The concept of linear dependence, though, is really defined differently. Okay. Now, then why would I bring this up? I've got one vector as a linear combination of the others, and I say this means that the three vectors are connected to each other in this way that's called linear dependence. This says that the three vectors are linearly dependent. But the strict definition of linear dependence doesn't say that a set of vectors is linearly dependent if one of the vectors can be written as a linear combination of the others. We're going to see that what I just said is a consequence of of the definition of linear dependence. If you're at all confused, don't worry about it. We're just scratching the surface here. So what I want to do is I want to look at the strict definition of linear dependence. Definition of linear dependence. It's going to be important for us on our road to figuring out a minimal spanning set. Okay, essentially, those three vectors, they don't form a minimal spanning set because the set is linearly dependent. Okay, so let's take a look at the definition of linear dependence. Linear dependence. So the strict definition goes like this. Let V1, V2, all the way up to Vn be elements of a vector space. Okay. The set V1, V2, all the way up to Vn is said, these vectors are called linearly dependent. And yes, we're going to abbreviate soon. LD. If and only if, or we could just say if, there exist constants C1, C2, all the way up to Cn, not all 0. So a set is a set of n vectors from a vector space is called linearly dependent if we can find, if there exist constants not all zero, such that C1 V1 plus C2 V2 plus all the way up to Cn Vn equals the zero vector. This is the definition of linear dependence. Now, let's go back up to my example where I said the three vectors were linearly dependent since one vector could be written as a linear combination of the others. Okay, I'm going to show you that that's completely in line with the strict definition of linear dependence. So what I determined above is that the vector 1, 2, one of the vectors, the column vector whose entries are 1 and 2, equals 1 times the first vector plus 2 times the second vector. Well, then that means that 1 times 1, 0 plus 2 times 0, 1 minus 1 times 1, 2 equals the zero vector. Okay. Now, take a look at the definition of linear dependence. A set of vectors is linearly dependent if you can find constants that are not all zero, such that C1 V1, let me write that here, C1 V1 plus C2 V2 plus C3 V3 in this case equals 0. I found three constants, not all zero, in fact none of them are 0, such that C1 V1 plus C2 V2 plus C3 V3 equals the zero vector in R2. Okay, so the idea of one vector can be written as a linear combination of the others is absolutely equivalent to finding constants that are not all zero, such that that final equation holds true. We're going to actually have a theorem that states that, and we'll prove it. We'll prove it for the general case. We see it for this case. We'll prove it for the general case. Okay? All right. So if a set is not linearly dependent, then the set is called linearly independent. So we have a closely related concept to the concept of linear dependence. It's called linear independence. So if V1, V2, all the way up to Vn are not linearly dependent, we say that they are linearly independent. Okay, and we'll be abbreviating that as Li. Linear independence, the opposite, if you will, of linear dependence, is a very, very important item. It's going to follow us through the rest of the course. Okay, so what does the strict definition then of linear independence look like symbolically? The vectors V1, V2, all the way up to Vn are linearly independent if the only values of C1, C2, all the way up to Cn, for which that vector equation holds true, C1 V1 plus C2 V2 plus ... all the way up to Cn Vn equals 0. The only constants we can find for which that equation holds true are C1 equals C2 equals all the way up to Cn equals 0. This shouldn't be too strange for you if you understand linear dependence. back to linear dependence. Vectors are linearly dependent if you can find some constants. If you can find constants, C1 to Cn, that are not all zero. That means at least one of those constants is not zero, such that C1 V1 plus C2 V2 all the way up to Cn Vn equals 0. So the opposite of that, linear independence, would be if the only constants for which that equation holds true are all zero. Okay? That is the V1, V2 all the way up to Vn are linearly independent if you set up the equation C1 V1 plus C2 V2 all the way up to Cn Vn equals 0. And that implies, if that equation holds true, that implies that the constant C1, C2, all the way up to Cn have to equal 0. The only constants that will make that hold true, that equation hold true, are all 0. Okay? Okay, so if you're lost, relax a little bit if you can, and let's take a look at some specific examples. This will clarify the concept of linear independence. So example, show that the standard basis vectors 1, 0 and 0, 1 are linearly independent. Show that we have a linearly independent set of vectors. Okay, now the definition for linear independence is right above. I'm going to change colors for it so that it's right in our face. Okay, so nice bright red. Vectors are linearly independent if, when you set up the equation C1 V1 plus C2 V2 all the way up to Cn Vn equals 0, the only constants you can find are C1, C2 all the way up to Cn are 0. So if that equation holds true, then all the constants must be 0. So let's set up the equation. Assume, oops, we don't need to be in red anymore. Assume the equation C1 V1 plus C2 V2 equals 0 vector. Show that the only constants that will make this true are C1 and C2 both equaling 0. Then you've got linear independence. So if we assume that equation holds true, that means that, well, we have the definition of scalar multiplication says C1 times 1, 0 is the column vector whose components or entries are C1 and 0. Similarly, C2 times 0, 1. And vector addition gives us that this is C1 and C2. And it's over. That is, C1 equals 0 and C2 equals 0. Two matrices are equal if and only if their corresponding entries are 0. This does it, QED. This shows that the set of standard basis vectors 1, 0 and 0, 1, I keep referring to them that way, that I shouldn't do that, that these two vectors are linearly independent. I'm using the word basis here as a calculus 3 definition, and some students may not have had Calc 3. So we've shown that these two vectors are linearly independent. So let's take a look at another one. Let's take a look at another example, just to get us used to the concept of linear independence. So let's show that the larger set, or in the earlier example, show that the set 1, 0, let's see, the set that contains 1, 0, 0, 1, and 1, 2 is linearly dependent. Linearly dependent. Well, let's set up the equation C1 V1 plus C2 V2 plus C3 V3, V3 equals 0, 0. Okay, so we have a set as linearly independent or linearly dependent if I can find constants that are not all 0 that make this that make this equation hold true. So let's set the equation up and see what we get for constants. Well, this says that C1 0 plus 0 C2 plus C3 2 C3, those three column vectors equals the column vector 0, 0. So combine to one column vector on the left, C1 plus C3, C2 plus 2C3 equals the 0 vector. Well, that means that the scalar equation C1 plus C3 should equal 0, and C2 plus 2C3 equals 0. Look what's come back to us. Look what this problem has resulted in us having to deal with. This is a system of equations. This is going to happen extremely frequently, whether we're dealing with linear dependence or spanning or whatever. Much of the theory results, much of the computations or the work results in a system of equations. This system of equations has infinitely many solutions. C1 equals negative C3. This is a solution. C2 equals 2C3. It's an infinite number of solutions depending on my choice for C3. Okay. Well, I'm going to be really explicit here. This system has infinitely many solutions. Many solutions. Well, it's a homogeneous system, so it automatically has a solution no matter what. It has the trivial solution, C1 and C2 and C3 all equal to 0, but this system has an infinite number of solutions. That means there are solutions. Now listen carefully here. This is extremely important. That means there are solutions other than the trivial solution. Okay, that implies, funny looking arrow, that implies that there exists constants C1, C2, and C3, not all 0, such that C1 times the first one plus C2 times the second one plus C3 times the first one, I think it was 1, 2, yes, equals 0, 0. This is very important. There exist constants that are not all 0, since this system, the solution to the system had those constants, and we have more solutions than the trivial solution. So we have constants that are not all 0 such that the equation holds true. Done. So the vectors are linearly dependent. So 1, 0, 0, 1, 1, 2, let's see, are linearly dependent. Okay. If the only constants you can find that solve the equation, the vector equation, are 0, linear independence. If you can find constants that are not all 0, you have linear dependence. Linear dependence. So another question. Example. Are the vectors 1, 1 and 2, 0 linearly independent? I don't know. Well, I do, because I know the answer to the problem, but assuming, well, I don't know. Set the equation up. C1 times the first vector plus C2 times the second vector. Set it equal to the 0 vector in whatever vector space you're in. We're in R2. Let's see what happens. Okay, well, let's translate this quickly into a system of equations. That's C1 plus 2C2 equals 0. C1 plus 0C2 equals 0. Now, I know we can solve this system instantly in seconds, but I want to bring up, I want to finish this problem using the theory that we've developed earlier in the course regarding the connection between systems of equations and the determinant of coefficients. If you missed that, don't worry about it. I'm going to show you now, right now. The determinant of the coefficients matrix for this system is equal to -2, which is not 0. If the determinant of a coefficients of a system of n equations and n unknowns is not 0, that means there exists a unique solution. This is from our past, and it's going to be a huge part of our future. If the determinant of the coefficients of a square system of n equations and n unknowns is not 0, you have a unique solution. This is a homogeneous system. Homogeneous systems always have a solution. That's all the constants equaling 0. Since we have a unique solution, this is very important, that implies that the only constants can be 0. The system has a solution, a unique one. It's a homogeneous system, and all homogeneous systems are guaranteed at least one solution. Therefore, that one solution that's guaranteed must be the only solution. And that solution is the trivial solution. C1 and C2 are 0. That implies linear independence. That implies that the vectors 1, 1 and 2, 0 are linearly independent. Okay. So you can kind of see why I insisted earlier that you, or I really strongly recommended earlier, that you don't begin this section without mastery of 2.1 and 2.2. Okay, so if you're completely lost, it's highly likely that you've skipped my advice and you've watched the video lecture for 2.2 and now you've decided you're just going to zoom into 2.3. Not a good idea. Okay, so are the vectors, let's take a look at another example, are x cubed plus x squared plus x plus 1, and n1 from P3, are they linearly independent? Okay. To help us with the notation, let's say v1, these vectors are v1, v2, v3, and v4. Okay, are they linearly independent? I don't know. So set up the equation c1 v1 plus c2 v2 plus c3 v3 plus c4 v4 equal the 0 vector from P3. The 0 vector from P3 we know from section 2.1 is 0. The polynomial p of x equals 0, or f of x equals 0. Well, let's see what this equation reveals to us. So this says that c1 times x cubed plus x squared, I believe that was v1, yeah, plus c2 times x squared plus x plus c3 times x plus 1 plus c4 times the constant polynomial 1 equals 0. Okay. Remember, we're trying to determine whether this set of 4 vectors from P3 are linearly independent. So we set up the equation that needs to be analyzed. We then translate this into a system of equations. This says that C1, well, that's the coefficient of x cubed. There are no other C1s in here. C1 should equal 0. the coefficient of x squared will be c1 plus c2. c1 plus c2, the coefficients of x squared. What are the coefficients of, oops, I put an arrow by x, I'm sorry. Get rid of that. Coefficient of x2. c1 times x squared, c2 times x squared, so c1 plus c2. And that will have to equal 0. Why does that have to equal 0? Because 0 is on the other side. Why does that have to? Why do those have to equal 0? People might not be sure about what I'm doing here. I'll back up a little bit. It might not be real clear how I'm getting those. Left-hand side. Left-hand side. Let's gather coefficients together. We have c1 times x cubed. My writing is getting really sloppy early. We have c1 times x cubed plus c1 plus c2, that's better, times x squared, plus, what are the coefficients of x? c2 plus c3 times x, plus coefficients of constants, c3 plus c4 times 1, equals the left-hand side. Equals left-hand side. 0x cubed plus 0x squared plus 0x plus 0. Okay? So, this equation is supposed to hold true for every possible value of x. So equate coefficients. Set the coefficients on the left-hand side equal to coefficients on the right. So c1 had better equal 0. So c1 plus c2, the coefficient of x squared, should equal 0. So c2 plus c3 should equal 0. So c3 plus c4 should equal 0. Okay? We have a system of 4 equations and 4 unknowns. I'm not interested in the actual solution. I'm interested in the structure of the solutions. That means I'm interested in knowing whether there is a unique solution to the system or whatever that's tied completely to the determinant of the coefficients, since this is a square system. It has 4 equations, same number of equations as unknowns. 1, 1, 0, 0. I'm computing the determinant. 0, 1, 1, 0. 0, 0, 1, 1. I have my graphing calculator to help. Don't do these by hand. Some people did the determinants on the last test by hand. That's ridiculous. You have technology, use it. That's what we're here for. Part of what we're here for. Okay, so the determinant of the coefficients is 1. We don't even need a calculator to do this one. That's a good spot check for you. This is an upper triangular matrix. Well, we don't need to go through back to the theory of determinants. The determinant of this determinant is equal to 1. 1's not 0. So that implies a unique solution. Implies we have a unique solution, and that solution must be the trivial solution because it's a homogeneous system. Every homogeneous system has at least the trivial solution. Since our solution is unique, all the constants must be 0. By the way, and I'm going to make this really official here. Really, you need to really tune in here for this statement because it has to do with your next exam. When you're showing linear independence this way, don't skip steps. Don't skip steps. That happened a lot on the first exam, and it really destroyed some exam scores. Don't skip steps. Don't skip logical steps. You set up the equation, c1v1 plus c2v2 plus etc. equals 0. You form the system of equations. If it's square, if you have the system has the same number of equations unknowns, you can fortunately use the determinant. If it's not square, you have to do something else. You have to do other stuff. You can't compute a determinant of a system of 5 equations and 17 unknowns. Okay. The theory says that, don't skip steps, the theory says that if the determinant is not zero, you have a unique solution. And since the system is a homogeneous system, that is, the constants are all zeros, that solution must be all the constants equaling zero. And that, and only that previous stuff, shows that the vectors are linearly independent. v1, v2, v3, and v4 are linear independent. Do not skip steps. Okay. Oops, there's no QED. It wasn't a proof. Okay. Oh, let me check where we want to go now. Okay, so let's return to clearing up a little bit of a mystery that we started out with earlier in the lecture. I stated in a particular example that since one vector, and here are those two vectors again, or those three vectors again. One of the three vectors was a linear combination of the others. But that's not what the definition of linear dependence looked like. The definition of linear dependence says that those three vectors were linearly dependent since I could find three constants, 1, 2, and -1, in this case, such that 1 times the first vector plus 2 times the second vector plus -1 times the third vector, I could find three constants, not all zero, C1, C2, and C3, that were not all zero, such that the equation held true. Well, it's clear that with this example, those two equations are absolutely equivalent. Absolutely equivalent. This happens to be true in the general case, though. Vectors don't always look like matrices, so we can't just make the assumption that since it holds true in R2 that it holds true for all vector spaces. But the proof of that holding true is pretty straightforward, and we're going to look at that idea as a very important theorem in your textbook. Theorem 2.6 from your text says, suppose that you have n vectors, v1 to vn, that are from a vector space V. Then those vectors, v1 to vn, are linearly dependent if and only if one of the vectors is a linear combination of the others. And the proof is instructive. The proof is very good for you, so I want you to see that proof. We're proving the general case that the idea of linear dependence and one vector being a linear combination of the others, those are absolutely equivalent ideas. Let's prove this. Let's prove the forward direction first, which means we assume that we're starting with vectors from a vector space and that the n vectors are linearly dependent. So suppose our assumption then is that we have v1, v2, all the way up to vn are linearly dependent vectors from V, a vector space. Okay. I want to show that one of the vectors is a linear combination of the others. Okay. Well, the definition of linear dependence says, so this implies that there exist constants C1, C2, all the way up to Cn, not all zero. That's the important part here. Not all zero, such that C1 V1 plus C2 V2 plus plus Cn Vn equals 0. I know that there exist constants. Some of those constants are not zero. At least one of those constants is not zero. Pick that one that we're guaranteed to be not zero. Suppose that, let's say, C sub I is not zero. Okay, suppose that now I can do that because since I'm assuming that the vectors are linearly dependent, that at least one of those constants is not zero. Suppose that one guaranteed constant, there may be others, is c sub I. Okay. Now let's rewrite the equation and isolate c sub I. This means that c1 v1 plus c2 v2 plus dot 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 all the way up to ci minus 1 vi minus 1 plus that one term where I'm guaranteed the ci is not 0 plus the next one, ci plus 1 vi plus 1 plus dot 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 all the way up to the end. So it's the same equation. I'm just writing out and isolating in that equation c sub I, v sub I. In fact, just so we can really see that we're just isolating that ci, vi. So we have those 8 properties from vectors, vector spaces. The sum of all the vectors except for the little red one in there, the ci, vi, the sum of all those vectors, they form a vector. So that if that vector, that little red vector in the middle, plus that other vector that's made up of the rest of the vectors is 0, that means that that one red vector is the opposite of the rest of them. It's a fancy way of saying add or subtract all the other ones except for that red one from both sides. But we have no such operation of subtracting something from both sides. Your author likes to do that, but we have no such thing. So that says that ci, oops, I don't know why I wrote that. That's really weird. I'll say it again. That says that I'm doing it again. ci, vi must be the opposite of the rest of the vectors. If the sum of two vectors is 0, then one is the opposite of the other. That's one of the properties. So that says that ci, vi must equal the opposite of c1, v1, or minus c1, v1 if you want, minus c2, v2, minus dot 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 minus ci minus 1, vi minus 1, minus ci plus 1, vi plus 1, minus dot dot dot, all the way up to minus cn vn. Well, if c sub I, v sub I equals that long vector on the right, then v sub I had better equal 1 over c sub I times that long vector. So that's a fancy way of saying divide both sides by c sub I, but we don't have any such concept of dividing both sides of a vector equation by anything. So v sub I should equal a negative c1 over c sub I v1 minus c sub 2 over c I v2 minus dot 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 minus c sub I minus 1 over ci v sub I minus 1 minus c sub I plus 1 over c sub I v sub I plus 1 minus dot 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 minus c sub n over c sub I v sub n. Okay. It's pretty ugly looking, but it ends that part of the proof. We don't want to get lost in what we were supposed to do. We're assuming we're approving the forward direction. That is, suppose that we have n linearly dependent vectors from a vector space. We want to prove that there exist constants that are not all I'm sorry. I got lost. Sorry. We're assuming that the n vectors were linearly dependent. We want to prove that one of the vectors is a linear combination of the others. I got lost in my own work here. And we just did that. We showed that vi is a linear combination of the others. We showed that implies that one vector v sub I is a linear combination of the others. Oops. Oh my goodness, my surface is going a little nuts. Okay. So now let's prove the other direction. Let's prove the other direction. For the other direction, what we're doing is we're assuming that which we proved in the first part, in the first direction. Assume one of the vectors v1 to vn is a linear combination of the others. So let's say, suppose that one of the v1, v2 all the way up to vn is a linear combination of the rest of the others. Oh my goodness. Of the others. Okay. So let's identify it. Let's let v sub j be that vector that's a linear combination of the others. So v sub j is c1 v1 plus c2 v2 plus all the way up to c sub j minus 1 v sub j minus 1. Skip over v sub j because it's the one we have a linear combination of the others. So plus c sub j plus 1 v sub j plus 1 plus dot 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 all the way up to c sub n v sub n. So we're assuming that one vector is a linear combination of the others. In particular, it's the v sub j one. We don't know where j is. It's just somewhere between 1 and n. And now we want to show that there exists constants that are not all zero, such that that original equation holds true. Well, if v sub j, that vector, equals the vector on the right-hand side, then you should be able to take the vector on the right-hand side and add the opposite of v sub j and get 0. What I just said is a fancy way of subtracting v sub j from both sides. But we don't have that operation. So again, if the left-hand vector equals the right-hand vector, then the right-hand vector plus the opposite of the left-hand vector should equal 0. I'm going to write that as our next equation. So that implies that the right-hand vector c1 v1 plus c2 v2 plus dot 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 plus c sub j minus 1 v sub j minus 1, I'm going to save a little room, plus c sub j plus 1 v sub j plus 1 plus dot 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 all the way to the end, c sub n v sub n, that's the vector on the right, plus the opposite of the vector on the left, so plus negative 1 times v sub j. I'll do that even in red, just so we can kind of isolate it in our minds, equals 0. Okay, now remember what we need to prove, that there exist constants c1 all the way up to cn, not all 0. I found one of those constants is not 0. I forced it not to be 0. C sub j is not 0. C sub j equals negative 1. So there exist constants c1, c2, all the way up to c sub n, in particular c sub j, not all 0. C sub j is not 0, such that c1 v1 plus c2 v2 plus dot 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 plus cn vn equals 0. QED. So the idea that one vector is a linear combination of the others, and there exist constants not all zero, such that equation holds true, they're absolutely equivalent. So linear dependence can be shown two different ways. Okay. What I decided to do is I'm looking ahead, and there's a lot of lecture left, and it's kind of involved. Is I'm going to break the lecture in this video segment into two video segments. So, and I'll write that up in the title for the video and stuff when I put it on YouTube. This will be the end of part one. Let's do that. This is end of part one of section 2.3. Okay. So as soon as you're done viewing this video, I think you should hold off on homework and then view part two. Okay, when you get a chance. Okay.